Peace be upon you and God's mercy and blessings. In this lecture, we want to see together how we can derive the compensation matrix. Let's now take an example together on a DON1 transformer, meaning we now want to derive the compensation matrix for the vector group which equals 1 for the one that equals 1. We learned in previous lectures how we can rotate the transformer. So now I have drawn a DN1 transformer. To derive the compensation matrix, what will we do? We will assume the presence of an external single-phase fault on the star side, and we will assume this 3 times. Once on phase A, once on phase B, and once on phase C. Let's start with phase A. If we assume the presence of an external single-phase fault on phase A on the star side, it will draw current in this manner. Consequently, it will draw a corresponding current from the delta side, also from the winding of phase A. However, due to the fact that your vector group equals 1, the external terminal connections cause the currents to now be drawn from phase A in the cables or the external circuit, relative to the transformer. This means they enter the winding of phase A and return again through the cable of phase C, so the currents will be in this manner. In the end, we can say that the current of phase A on the star side will draw a corresponding current of phase A on the delta side at an angle of 0, and a current of phase C at an angle of 180 degrees. That's the first part. The second part is the relationship between the magnitudes of the currents now, since on the delta side, only this winding has currents drawn from it, while the other windings have nothing drawn from them. This will make the line current the same as the phase current. So what is the phase current equal to? The current on the high side will equal the voltage on the low side as a phase over the voltage on the high side as a phase multiplied by the low side current, or the phase of the low side, which is the phase A current, since on the low side the phase equals the line over the square root of 3. Substitute it with the line over the square root of 3. On the delta side or the high side, the line is the same as the phase. Therefore, you will find that the relationship between the phase current in the delta and the phase current on the star side is that you divide the line voltage of the star by the line voltage of the delta, but it will be divided by the square root of 3. In this case, as we agreed, the line current is the same as the phase current. What are we going to do now? Our compensation matrix, we know, is a 3A3 matrix. And now I have the current that went towards the low side, which is only the phase A current. So, where do I get the numbers that are here from? From what we just said. I know that if a current is drawn here in the star towards phase A, it will draw in the delta from phase A and phase C with an angle of 0 and an angle of 180. So here we can say plus, and here we can say minus, and let's say plus. Also, there's another thing. We know that the current towards the high side will be divided by the square root of 3, right? So, how do I place it here? For phase A, I put 1 over the square root of 3. For phase B, I put 0. For phase C, I put negative 1 over the square root of 3. This means 1 over the square root of 3 is a common factor outside, and I have 1, 0, negative 1. In this case, if you multiply the matrices together, it will eventually show that IA over the square root of 3, 0, negative IA over the square root of 3. Thus, indeed, just like a delta, connection has current in phase A and phase C. I found that on the star side, despite having only one phase, it compensates in phase A and phase C. And here I will find IE over the square root of 3. And here negative IE over the square root of 3. And here also the current will be divided by what? Divided by the square root of 3. Now, someone might say, well, this is positive and this is negative. And here also this is positive and negative. How when you add them together, will it equal 0? I would say you forgot something, that the current in physics is magnitude and angle. And let's not forget that the result of the current is moving in this direction towards the star side, and as a result of the CT present here, its star point is facing the direction of the transformer, which is the protected object, and the polarity of the CT subtracts polarity, and the other end of the CT is expanded to the dot point in the relay. You can refer back to all of this in the previous lectures, and we will know that the current is actually at an angle of 180 degrees. This means that the value you get here will be negative, and here it will be positive, which is the opposite of positive and negative here, and thus I reach the stability stage. Okay, let's see this. After that, we will apply an external single-phase fault on phase B, and consequently the current will move like this, drawing a current from the winding in front of it. The transformer on the delta side on phase B, and thus I will find that the currents are drawn from the cable externally from phase B, passed through the winding, and returned from the cable of phase A. This means that the current of phase B on the star side is opposed by the current of phase B on the delta side at a 0-degree angle, and the current of phase A at a 180-degree angle. I will then place the matrix and leave the middle column, which I will start discussing. As we agreed, I have phase B at a 0-degree angle, so I put 1 here, and I have phase A at 180 degrees, so I put -1 here at the top, and phase C I put at 0. Don't forget 1 over the square root of 3, so I have 1 over the square root of 3, -1, 1, 0. Therefore, if I multiply this together, I will find negative AB over the square root of 3 plus AB over the square root of 3 and 0. Therefore, I will find here that the phases A and B have reversed, like in the delta phases A and B. I will find here a negative, but don't forget that IB is at a 180-degree angle, so it becomes positive and this negative. Here you have IA negative, so here IA becomes positive and here IB is positive. So I will find here that IB has become negative, and thus I have also reached the stability condition. Then I go to phase C, where you also have the presence of an external single-phase fault, and the current drawn in this direction will also draw from the phase C winding. Consequently, it will be drawn from the phase C cable through the winding and return from phase B. This means that the current of phase C on the star side will draw a corresponding current of phase C at a 0-degree angle on the delta side, and the current of phase B will also be at a 180-degree angle on the delta side. Consequently, I will also set up a 3 cos 3 matrix, and here I will start arranging the third column, which, as we can see, is the current of phase A at 0. The current of phase B here will be -1, and the current of phase C will be +1. Don't forget the 1 over the square root of 3 for the magnitude of the current. Therefore, if you multiply this together, you will find that you have E0 negative IC over the square root of 3, IC over the square root of 3. Don't forget the angle of IC will be 180 degrees, meaning this value will be positive and this value negative. P is positive, C is negative, P is negative, C is positive. I have reached the stability condition. Very nice. And thus overall you will find that matrix number 1 has become 1 over the square root of 3, and you have 1, 0, -1, -1, 1, 0, -1, 1 multiplied by AAABAC. Very nice. Now we want to talk about a very important point. Now we have something that is always mentioned in the manuals of protection relays, which is the KVG. The KVG, quite simply, is a constant or a factor for the vector group. And we always see this table present in any manual. So, what is this table about? This table imposes different types of faults, whether they are 3-phase, 2-phase, single-phase with inode elimination, or single-phase without inode elimination. 2-phase, single-phase with inode elimination, or single-phase without inode elimination. Then, after that, you have a column for the reference winding or the high voltage, which I will find similar to the even vector group column. Very nice. Here, we will find that the vector, which is your KVG, is 1 or more. In the case of 1, in the case of 1.5, in the case of 1, in the case of 1, in the case of 1. Then I will go to the other side of the transformer and see what my vector group equals. Is it an even number? 0, 2, 4, 6, 8, 10. So I will substitute these numbers. Or is it an odd number? 1, 3, 5, 7, 9, 11. And I will substitute these numbers. Okay, now we have taken an overview. So what is this KVG actually? The KVG is essentially the inverse of the compensation matrix, the inverse of the compensation matrix. Let's mention a small piece of information and then we'll go see how to derive all these numbers. The current that is used in the calculations is supposed to be the current divided by, then all of this is multiplied according to the base current in amperes. Then all of this is multiplied by a 3A3 compensation matrix according to the vector group. To simplify the testing of protection relays and to avoid using a 3A3 matrix, I derived something called KVG, which is the inverse of the compensation matrix. Therefore, the relay current will equal the measured current in amperes divided by the I base in amperes. And instead of having the compensation matrix in the numerator, I place the kVg here in the denominator. Let's see how the numbers inside this table were derived. You now have the compensation matrix, which can be even. Let's take example number 12, the matrix number 12. It can also be odd, and let's take the example where the vector group equals 1, or the matrix of the vector group equals 1. Let's consider the 12. If I assume that I have a single phase fault with E-node elimination. So now I have assumed with you that I have a single phase fault or a fault on phase A, and B is 0 and C is 0. In this case, I will find that the current of phase A is multiplied by 2/3. And since the kVg is the inverse of the compensation matrix, it will be 3/2, which is 1.5. If you have a phase-to-phase voltage, meaning current from phase A, and returning from phase B, meaning both are equal in magnitude, equaling I, and the current in phase A is 0, and the current in phase B is at 180 degrees. We assumed with these numbers and C equals 0. In this case, you have 2IA minus IB, and IB is originally at an angle of 180, which is considered 2IA plus IB. So it becomes 3 because IA and IB are equal, both being I. So you have 3I over 3, which equals 3/3, equaling 1, and its reciprocal is also 1. Now, if you have a three-phase fault, meaning IA, IB, and IC, let's assume I at an angle of 0, I at an angle of 240, and I at an angle of 120. In this case, you have 2I at an angle of 240 and at an angle of 120. In this case, you have 2 minus I at an angle of 240 and minus I at an angle of 120. Of course, we know that since IB and IC have 240 and 120 between them, meaning there is a 120 degree shift between them, their sum will simply equal I at an angle of 180 degrees from phase A. And since they originally have a negative sign, their sum will equal plus I. And you have 2 times I, which is from IA, so you have 3I over 3, which means overall your factor will equal 1. So let's deduce here. In this column, if I have a single phase fault with E-node elimination with an odd vector group, the phase voltage with an odd vector group, I will come here and tell you that you have a current or fault on phase A with a value of I, and there is no B or C, so at that time you multiply 1 by I over the square root of 3, and of course 0, 0, right? So it's 1 over the square root of 3, which is its reciprocal, the square root of 3, which is 1.732. Now let's assume a phase-to-phase voltage, meaning I at an angle of 0, I at an angle of 180, and here 0. So I minus I 180 is 2I on islands 3, reciprocity is 3 on 2, equals 0.866. For a three-phase fault, I 0, 240, 120, multiplying gives 1 in I, which is I. I at an angle of 0, I at an angle of 240, I at an angle of 120. If you multiply it like this, you find 1 times I, so it becomes I negative 1 times I at an angle of 240, then 0, I find that I minus I at an angle of 240. In this case, if you subtract these two from each other, you get square root of 3I, square root of 3 over square root of 3 gives you 1, and this is the vector written in front of you here. So quite simply, I can deduce the compensation or the vector group of your compensation matrix to facilitate your calculations during injection on the protection relays. Protection, release. Very nice. Okay, some people have asked me about the idea of seeing a strange number here, which is the concept of I-node elimination, and they come and ask what exactly is this 1.1 and where does it come from? Let's take a look together. Alright, now in the Siemens manual, we find a table like this. Of course, this table is among a group of other matrices. Let's focus on this table. This table tells you that the neutral point of the transformer can be isolated, can be grounded, and its IE is not measured and is unknown, or it can be grounded. And the IE or the current of your neutral is measured through a CT installed on the transformer's neutral. Alright, and I will now focus only on vector group number 1. It tells you in this case, this is the matrix you will use if it is isolated. If it is grounded, this is the matrix you will use. If it is grounded and IE is measured, this is the matrix you will use, but initially, this matrix is matrix number 1 that we all know. If you have a D-Wen1 transformer, then, in this case, on the star side, your currents will be multiplied by which matrix? By matrix number 1 in this manner. Very good. Now, Regarding the other matrices, let's first take a look at the form of these matrices. What do these matrices tell you? If you have a single phase fault without inode elimination, in this case, it means you have a current, for example, on phase L1, and the other faulty currents are at 0. Therefore, if you multiply this by 1 plus the square root of 3 in IL1 plus 0, you end up with 1 plus the square root of 3 over 3 in IL1. This is outside the matrix. How does it evaluate the situation? It equals 3 over 1 plus the square root of 3. And this is what we found on the previous page, the factor that was 1.1, which we were puzzled about. And we can deduce anything else we want in this manner. Nice. But right now, I want to focus on the part about the matrix that we're talking about. Initially, there's a very important point here. You have a neutral point isolated, so you shouldn't actually say that you have a single phase to ground fault. It's appropriate to start by telling me that you have a two-phase or three-phase fault. Nice. Okay, let's first see what this matrix is. If you take this matrix and want to divide it and see exactly what its conditions are, you will find the following. If you notice here, at every point in this matrix, you will find that the number 1 has been added. If you remove this one from all the existing ones and the rows you have here, what will you find? You will find that the number 1 appears. What does that mean? Let's see together. The square root of 3 over 3, which is 1 over the square root of 3, 1 over the square root of 3, negative square root of 3 over 3, which is negative 1 over the square root of 3. And here you have nothing, so it's 0. Then here you have nothing, so it's 0. Here you have part 3 over 3, which is 1 over part 3, and so on. You will find that here you have a matrix number 1. And what about the rest? The rest you will find is a set of 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 over 3. So it's 1 over 3, and the entire matrix is 1s multiplied by IA, IB, IC. 111, 3, so it's 1, 3, and all of it 1s multiplied by. If you break down this matrix, you'll find you have IA plus IB plus IC over 3. Who is this? This is the neutral current, and similarly on the other side, or the terminals meaning red, yellow, and blue, you'll find that all of them show the neutral current. It's as if you've combined your regular currents with the regular compensation matrix plus the neutral current, which is added each time. So if I go back here, it means that you will have, and what does it mean? It means if you came and told him that I have the transformer, or just told him now that the current has been read, and we will see this when we apply this to the current that has been read from being installed on, in this case. It has been read from the CyberCity installed on, in this case, how will the relay handle it? It will take the fault current on the transformers and multiply it by the large matrix because it is supposed to receive 1 over 3 in the neutral current. You see 1, 3 in the current of what? In the neutral current, which is IY, which is the neutral current, IY, IY, IY. And of course, IY will be at a 180-degree angle from the IY present here, and thus you have cancelled out IY with IY as if you performed inode elimination through what? By using separate city and using the matrix you see in front of you. And with that, we have understood what this matrix means and how it was derived. Okay, one more additional piece. If you have an isolated system and you assume that you now have two-phase or phase-to-phase voltage, let's see. We said we don't have single phase anymore. We have two-phase, meaning IL1 and IL2 at angles 0 and 180, and you don't have IL3. In this case, you have 1 plus square root of 3, I plus 1 minus square root of 3. But let's not forget that the I here is at what angle? It's at an angle of 180 degrees, meaning it's like saying 1 plus square root of 3 minus 1 plus square root of 3 over 3. So the 1 cancels with the 1, and square root of 3 plus b. Square root of 3 becomes 2 square root of 3 over 3. So it becomes 2 over square root of 3. Where have we seen this before? If we go back, I will find 2 over square root of 3, which is the reciprocal of square root of 3 over 2, which is in the case of whom? In the case of, am I right? So now I understand the whole game and I can deduce any loan.